Thank you. Hello, everyone. My name is Jong-Hyun Yoon, but you can also call me Jay for short. I'm a postdoctoral researcher at Sungnan National University in Daejeon, where I started in September. Now, I'm here to give a seminar talk titled Modern Computational Approaches to Early Universe Modeling. Firstly, I'd like to thank our Professor Skopal for kindly inviting me here, and also everyone for coming to see me. I'm also very pleased to revisit my alma mater, Sungnan University, after a long time. And it feels great or meaningful to now be here as a seminar speaker. So today, given the rapid advancement in computing and related areas, I'd like to talk about how high performance computing can be applied to address different problems in the early universe. So here's the outline for today's talk. I'll start with a brief intro to the early universe. This will provide usable context for what we are going to discuss next. And then we'll delve into how particles could have formed in the very early universe. So I show that particles could have been produced solely through gravitational effect, without any other interactions with other fields. And we will also approach this numerically using a high performance computers, and when the particle production is efficient, we have to solve the system through lattice simulation. And then we apply the simulation outcome to address different problems, including the documented problem. And we will cover another example of using the simulation outcome. And lastly, I will introduce how we can go further by using one of the hottest techniques today, machine learning. You may have heard that this year's Nobel Prize in Physics was awarded for research in machine learning, related to machine learning. So the basic idea here is very straightforward. Wherever you have data, machine learning can be useful, especially when the data exhibits some patterns. So we can generate data as much as we want through lattice simulations. And the data we make is not random. So for instance, the distribution of fields like Higgs fields with gauge interaction or self-interaction can be understood through kinetic theory, which implies some patterns that can be analyzed by machine learning. So in the conclusion, I will wrap up with a summary of the main points. As you can see, this talk covers 3 different papers. So if you are interested in more details, please feel free to have a look. So we believe in the Big Bang theory, which suggests that our universe was a hot dense plasma state that cooled down to form matter and structures like we see today. However, before the emergence of the hot dense plasma, another important cosmological event should occur, which is the rapid expansion of space or cosmic inflation. So the need for inflation hypothesis arose because the conventional Big Bang theory has some issues known as horizon and Fleming's problem. But long story short, introducing inflation in the early universe explains why our universe is so uniform, and why there are also small inhomogeneities. And the most popular inflation theory, it describes inflationary dynamics in terms of a real scalar field called inflaton. So the inflaton's flat potential can lead to inflation, making the universe uniform, while quantum fluctuations of the inflaton field explain the small inhomogeneities. So without these inhomogeneities, matter would not clump together to form structures like we see today. So this is how so-called inflation cosmology was founded about 50 years ago. So the key question here is what could happen between cosmic inflation and the formation of the hot dense plasma. So the transition between these 2 events is called reheating. And since little is known about how reheating occurred, we can think of different reheating mechanisms. And the simplest written mechanism involves inflaton decays into Higgs particle. Since Higgs interacts with other known particles, we can easily explain written mechanism. However, the inflaton field is believed to transition to the minimum potential after inflation with large field value, and it would oscillate around the potential minimum, as you can see here. And this can lead to some turbulent and non-perturbative effects like resonant particle production, etc. And we call such effects and the relevant regime preheating to distinguish it from reheating. So based on this, we can think of simple dark matter production scenarios. That is, while the inflaton field decays into Higgs particles and leaves the universe, dark matter is produced during preheating. So we need dark matter and the inflaton field beyond the standard model. So in this framework, the simplest dark matter scenario would be inflaton being dark matter. And the next simplest case is dark matter production via interactions with the inflaton, and so on and so forth. And the last possibility, or the sequel to this series, would be dark matter production via gravity without interacting with other fields. And this is what we are going to discuss in more detail. So we can examine the action for this model. So this model contains two scalar fields, one for inflaton field and another one, the other one for the scalar dark matter denoted by S. And this this dark matter couples to gravity or Ricci scalar with the interaction strength psi. And this term is pretty well known. It's known as nominal coupling to gravity. Since R is a function of the energy of the system, which is dominated by the inflaton field, with dark matter and the inflaton field could indirectly interact. We can also discuss how the nominal coupling term, or NMC term, could generate the dark matter. So we first write the equation motion for the field F for this space-time, and neglecting such rescattering or back reaction of the produced particle, we can re-express this equation in momentum space like this. So K denotes the co-moving momentum for different modes. So what's important here is the frequency term in the middle. So this is the second order differential equation. And when the frequency term is positive constant, the solution will be just oscillatory one. While if this term is negative constant, you have exponential solution, which indicates particle production. So interestingly, even without such nominal coupling, because of this removable term, this frequency term can be still negative for very small values of K. So you could have some particle production for small K modes. And when this psi is 1/6, this two term could cancel out. So you have a stable solution for this case. And lastly, when psi is very large, we could have some explosive, we could amplify gravitation production of particles. And there are various approaches to solve this system quantitatively. So the scale factor, since the scale factor denoted by A evolves differently depending on the equation of state. So we can divide the expansion period and match solutions at each boundary, each one approach. And you can also study resonance structure in this equation. And however, we would like to solve this system fully numerically using HPC. So basically what we want to do is to solve this equation for different values of K simultaneously using high performance computers. So I'd like to demonstrate how to use HPC in a nutshell. So first, you need the access rights to HPC. So most universities have their own HPCs, or they could share it with other universities. So you need to apply for it first. And once you have an ID, you can access the HPC via SSH, which is a remote control tool. And then you can either write code by yourself or use built-in or pre-made codes. Although you cannot use the root account, which is an administrator account on this HP system. Instead, you would load modules and run the code using a Slum workload manager. And each usage or protocol is universal. So once you adapt it, once you learn it, you adapt it to other HPC environments.
I mean, what does it stand for? HPC.
High performance computers or computing. So afterwards, you want to refine and interpret the output as you want. So I'd like to show you a demo code that I prepared, which solves the equations of motion that we discussed earlier. So first, we start by importing NPI libraries for parallel computations. For these libraries, you need to set up your own Python environments locally, not globally on the HP system. And you want to define a function to solve the equation motion that we saw before. And here we assign ranks to different processors to distribute tests. With rank 0 handling the standard input and output. So as you can see here, we want to solve 160 equations of motion using 160 processors. And in the end, rank 0 will write the output. And this code is submitted to the scheduler, as you can see on the right. And this is script.
Script is in Python, right?
Yes. So it's pretty straightforward. That's why I'd like to share it. I mean, I just wanted to say it's not that difficult or esoteric. Using HPC is not something difficult.
Okay. Actually, why do you introduce those skeleton define? And also ask why you introduce those skeleton define nature?
It's the inflaton.
Why is it?
Yes. Oh, maybe I should have.
S.
As for the scalar dark matter.
In the action, the potential.
We can check the action together.
Potential is yes.
So phi is hidden in R in the energy momentum tensor.
Yeah, exactly. Yeah, that's a problem. Is actually a function of the energy density of the system, and it is dominated by the inflaton in the early universe. So they could indirectly interact, not direct interaction. Thank you. Where were we? Yes.
Documenta is no scalar.
It is
no
scalar.
potential and no potential.
It can have, but it's negligible. You need to assume some potential, but it is negligible in this model. It could have mass and self-interest.
Are you thinking of axial dark matter, or it could be any scalar?
It could be any scalar. We don't assume action. Okay, so this script allocates computing resources and it loads modules and run the code. We can move on. And here's the demo result. And the mode solutions are actually converted to occupation number, which corresponds to distribution function. So when integrate over K, this gives a particle number density. And it's not explicit here, although not shown here, we solve this equation during inflation and up to a certain point after inflation. So we found that there's no production during inflation, but only after inflation. And however, there are some limitations in this approach because we have neglected the back reaction or rescattering effect of the produced particle. But if psi is large, the production of dark matter would be very turbulent. So they could rescatter and back react to dark matter and the influence of field as well.
I
So-
don't have direct coupling. So there is a direct coupling between the S and the coupling photon.
In this model, no.
So once we produce this scalar particles, when you say they back react, through which you direct?
So the R itself could be, I mean, R is a function of the energy, right? So the dark matter could make up the energy of the system, so it can affect the evolution of expansion.
Usually the energy momentum tensor is dominated by new platform, but later, in principle, we don't know.
We don't know, so we cannot do analytical computation. Thank you. So the point is, we cannot rewrite the original equation of motion in momentum space, because now back reaction and rescattering effects are important. So we have to go back to the original equation of motion, well defined in 4D space time. So to this end, we solve the original equation of motion in a virtually created space. So this approach is called lattice simulation. So in lattice simulations, we solve equations of motion for different fields like this, and you also take into account, you also consider freedom equations to account for the expansion of space. And there are important, let's say, simulation parameters like L, the length of the grid, and the number of points, and they are related to the momentum window through which we can observe physical events. For instance, the minimum momentum that we can capture is inversely proportional to the length of the grid. And the maximum one is proportional to the number of grid points, which scale with the simulation time. So the larger momentum window you want to have, the longer simulation time you need to take.
Friedman equation should have a correction from your slide.
That's very good question. Yes, actually, for that model, we need another equation. So I kind of cheated here. I neglected this stuff, but actually in the code, there are some complications because of the nominal coupling term. So we have to rewrite the simulation code for this particular model. That's why we use a code called Cosmo lattice, which already kind of optimized or customized for the nominal coupling terms. So below us, so there are plenty of codes for this purpose. So among them, we use Cosmo lattice, which came out a couple of years ago. As you already pointed out, you have to optimize the code to take into account the nominal coupling effect. So this code features all the other functionalities. So that's why we use this code. And below are the simulation results. And the first figure represents energy distribution of the two fields, the influence field and the scalar dark matter. And the next figure in the middle represents the evolution of R or each scalar, which indicates some collapse after a while, after inflation. So this is one of the reasons why we cannot rely on conventional analytical estimates. And the third figure represents variance of the scalar dark matter, indicating explosive particle production. This A denotes the state vector. So as you can see, simulation results help us intuitively understand what could happen in the very early universe. Not only that, we can also use numbers obtained through the lattice simulations to explain dark matter. So for that, we have to take into account all the experimental constraints. One of them is dark matter relative abundance. which is set during radiation dominated era. To make a radiation dominated era, we have to assume a Wheaton channel. So for that, we assume inflaton decay into Higgs particles. And this is the final figure, which is available parameter space in terms of the psi interaction strength for the nominal coupling term and the reaching temperature. So one thing that we can immediately capture is that a larger psi increase the dark matter production. So we have to dilute them by having longer expansion of space. So this is why we have a lower reaching temperature for larger psi. And another thing that we can see is that the result doesn't vary much beyond a certain value of psi. This is because the total energy of the system is fixed, and the scalar dark matter, the energy of the scalar dark matter cannot exceed half the total energy. That's why that
decoupling limit, large psi,
decoupling limit.
of your dark matter.
Oh, well, no, it's more like saturation limit. The interaction is too strong, so they could have like a 50-50 energy distribution. I mean, dark matter and the inflaton.
Have you considered negative psi?
Yes. But depending on the sign, the production could be efficient in other regime. I mean, during inflation, it could be very efficient.
Your dispersion relation, I mean, should be tachyonic or large.
Yeah, that's the problem. So for that particular case, we have to go back to the time of inflation. So in this model, we consider particle production after inflation. So for positive psi, it is okay. But for negative one, you have to integrate the equation from during inflation. The result highly depends on the sign of psi.
So how many free parameters do you have? So what do you fix and what is the output? Because the radiating temperature is an output.
It's an output. There are some parameters you have to adjust.
So 4 parameters, yeah.
Yes. For instance, mass of the dark matter and the self interaction, and so on. The mass of the inflaton field. There are a few.
That are not in this 1 GeV. Yes. In this particular case.
How do you select the mass of the inflaton and scalar field? So you get some number, yes? How do you select them?
We take it from inflationary data. It has to be the CMB data.
Is in upon the resolution, yes? This spot size, yes? Angular size, is this distribution? No. How do we get it?
This has to do with the energy scale of inflationary system fixed by CMB.
But then you were saying about W net, but Planck is more accurate. In the beginning of your talk, you were telling that it is based on W net, but
Yeah,
now
but
we
there are
have
some-
some data, Planck data is more accurate.
There are some freedom in choosing this number because we are talking about particle production after inflation. So this inflaton potential doesn't need to be the same as the inflaton potential for inflationary region. So there are small free range flexibility. So this is the end of the first example of using simulation outcomes. Now we move on to the next example. So now we forget about dark matter. We just focus on how to make simple and general inflaton potential and Wheaton channels, since we don't know anything about Wheaton and inflaton potential after inflation. Then we can get something like this. The inflaton potential is a now monomial function, and K is a power of the potential. And we have interaction channels to the standard model radiation like this way. So inflaton decays into fermionic particles or bosonic particles, and scattering. You could also consider scattering of the inflaton field and bosonic particles. And then you want to find the time for reheating. So we can define reheating as a point when the radiation makes up most of the total energy of the universe.
R is radiation.
Yeah, so R stands for radiation of standard model, RH for reheating. And during inflation, because of inflation, the energy of the universe is concentrated in the homogeneous part of the inflaton, or we can call it condensate or background of the inflaton field. So fluctuations are negligible during inflation and right after inflation. So using this, we can work with this. We can work with the classical oscillations of the inflaton, and we can determine the corresponding decay rate using the classical inflaton background. And this allows us to proceed with analytical computation to find the time for reheating. So A represents the scale factor. So AN means the end of inflation. This is how we can compute the time for reheating or the scale factor for reheating. However, there's a problem because as time goes on, the inflaton background will transfer its energy to inflaton particles even without any other interactions. It's just because of its self-interaction. So this can be captured through lattice simulation. So you can see the figure that the energy of inflaton particles were negligible in the beginning, and then it will dominate the total energy density of the system in the end. Yellow for particle and green one for condensate, the background, classical background inflaton field.
So the blue line is just
Total one.
diluted to what?
This decrease in behavior is just because of the expansion.
Yeah.
So what's important here is the ratio of the different energy densities. So now the order of events the order of events is important. So if fragmentation is, if this phenomenon is called fragmentation, I should have told you that this collapse of the classical background is called fragmentation. So when this fragmentation occurs early, we cannot rely on the conventional analytical estimate that we have considered before. Using the classical inflaton background, etc. We cannot use it if this happens early. So if fragmentation is slow, we cannot rely on the conventional approach. However, if fragmentation is slow, we have to reconsider rescattering such that now inflaton quanta or particles decay into standard model radiation, not from the inflaton background. And the figure on the right is the final result, showing the summary or the main points. So larger Y increases production rate for reheating. So reheating happens earlier, resulting in a larger reheating temperature, as you can see. And if Y is small, then reheating will be delayed with the decay rate. And then we have to reconsider reheating such that now inflaton particles decay into radiation with the decay rate being proportional to the mass of the inflaton field. then reading will be delayed. It is so delayed that the resulting reading temperature will be too low to meet constraint by a BBN.
Hey, the different colors we can do.
This A for the A denotes the power of the inflated potential. So we have considered different powers of the inflaton potential and different reading channels and so on. Okay.
It means that power is large, you have a lot of cell interaction.
Yes. So, so from this figure, we can conclude that when K is larger, fragmentation occurs later. So this has to be this point has to be the time for fragmentation due to self-interaction. So yeah, fragmentation is more important for smaller K because now we have to consider reading through inflaton particle decay from here. So this is a kind of these dotted curves are conventional approaches, while these curves are for particle decay, inflaton particle decay to standard model radiation.
How should one read this plot? I mean, there is BBN, there is a gray area.
Mhm.
And when the curve drops on BBN means what? That you produce too
We
much.
should exclude it because reading temperature is too low. I mean, we need a certain value of reading temperature to explain BBN phenomena.
I know that there are-
Yeah, it's yeah, exactly. So it's around MeV. As you can see, it's 10 to minus 2 GB, which is around a few MeV. So these gray areas must be excluded.
And in the axis, what do you have? Is 10 minus 4, 10.
In this axis,
Yeah.
I represent the strength of the coupling for permanent reheating. It looks like you got coupling.
Again, here, how many free parameters you have in this? So Y, K, and what else? Yeah, nothing else?
In this model, we have only K because all the other parameters are fixed by
Potential is
CMB data.
Yeah, very
Why
good.
in power K?
Yeah.
Because it is already fixed by this effective potential, and those conditions are set to explain CMB data.
Where is your document?
No, this example has nothing to do with that. It's another example. Now we are moving
example.
Yes,
Other paper.
yeah, it's another paper. But when I start the new topic, I just put citation. So you can refresh your mind.
Have you considered reading potential around the vector waveline? I mean, that one.
So I consider
So that potential is a approximation of the original infrared potential, right? Or around the vector.
Yeah.
Is-
it's kind of effective potential.
That's correct.
Right? Follow the question?
I mean, that potential should be the approximation of the infrared potential around the vector.
Yeah, it's kind of effective potential after inflation. So
Yeah.
we don't explain the inflation region here.
Yeah,
We
so
only focus on particle production after inflation.
yeah, I think you wanna check how impact the power of the potential would affect the particle production, right?
Yeah, this work has to do with such relationship yes,
So,
between K and the particle production.
You assumed to find out some special K or something. Because according to the graph, the next slide. Yeah. It seems like the case of the case when k equals 4 seems something special.
That's more significant than
Yeah,
other
yeah.
cases.
Because there's a rule like as the k increase, the turning point of the curve goes to the left, right? Turning point, but actually the critical point moves in a different manner, right? So the k equal 4 is kind of more meaningful other than the other cases.
Yeah, that's right. So this has to do with the how efficient fragmentation happens. So K4 in this case is the system is conformal. So production is more efficient, which means fragmentation happens much earlier than the other case. So it in fact are more significant than other values of K.
So it seems like very interesting because if we have the Stravinsky implantation around the vacuum, actually we're gonna get some quadratic potential around the vacuum, but have you just neglect the k equal 2 case or?
Yeah, because it doesn't generate self-interaction for the quadratic implementation.
I see. Then your scenario is kind of independent of the Stravinsky case, right?
Yeah, you can say that it's slightly different from the partial model.
And so is it correct to say that if you compare the dotted lines with the solid
Solid
lines, yes, the dotted lines are just an analytic calculation without back reaction. They don't have any exclusion. But the breathing temperature is always above 100 G, no matter what lines, right?
Maybe it could be excluded on the left.
Yeah, very small couplings. But here you have a dramatic effect.
Because of fragmentation.
Fragmentation excludes models that will be allowed. Yeah, but so anyway, so if you have a coupling which is just quadratic, there is no.
Yeah.
So this is really due to the circle.
It's a self-interaction. So thank you all for pointing out those important points. And then there are other applications for using information outcome. We can also tackle some theoretical problems like unitarity in different inflation models. And as you may know, there is active research on gravitational background. After inflation, particle production after inflation could lead to some large energy contrast in the early universe, which can result in gravitational wave background, and it can be observable depending on the model. So it is very important for probing early universe physics, and we can also gain some intuitive insights by making an animation of this particle production. So this is an animation that I made 2 years ago for symposium in France. And lastly, one of our ambitions is to fully simulate the entire early universe. We could reproduce heating or some radiation of the hot dense plasma state. This is the final topic that I want to discuss now. And before moving on, let's take a short digression. So you have just heard that from me that this year's Nobel Prize went to researchers in machine learning, and there was a debate on whether machine learning qualifies as physics or not. But personally, I just found it exciting because my last work is related to machine learning and the early universe. So how is it related? So we wanted to simulate the entire early universe using two lattice simulations, but the problem is that the simulation tools are designed to study effects in pre-reading region, whose time scale is much shorter than that of the entire reading mechanism. And another problem is the momentum window through which we can observe physical events is highly limited. Of course, you can extend it, but you just take more simulation time. However, the good news is that the later stages of operating system exhibit some universal patterns. For instance, the distribution of field like Higgs with gauge interaction or self-interaction could evolve in a self-similar manner. So this can be studied. This was studied by Misha and Chaker. And this is the distribution function of phi field in biquartic model, which exhibits some patterns and trends as well. So
What is eta? Eta is
eta is a co-moving time variable. And this is the rescaled distribution function. Okay. So considering patterns and trends, what could come to mind? Deep learning excels identifying patterns and trends. So basically, we try to extrapolate simulation outcome using deep learning technique. So let's briefly discuss deep learning. It is often mentioned alongside AI and machine learning, which can be confusing. So this diagram shows that the AI is the broadest concept, with machine learning, with the deep learning being the most specific one. So AI refers to artificial intelligence, while machine learning and deep learning are kind of methods to achieve it. And the main difference between deep learning and machine learning is that deep learning uses neural networks. And I became interested in deep learning because it mimics human neural processing. And choosing the right network for the problem is crucial. The data we are going to handle are distribution functions or fields. And they can be viewed as images with specific patterns, making convolutional neural network or CNN the most relevant choice. And CNNs are specialized for image analysis using filters to extract important information from image files. So for instance, in this cat photo, the parts that make it recognizable as a cat are identified by the filters, which scores high values on this important area. And those are analyzed by multiple layers, and you can draw a conclusion on whether this image depicts cat or dog. And another interesting feature of deep learning is its ability to combine with other neural network. And we need a long short-term memory network, as we require not only local patterns but also long-term trends in the evolution of distribution function. So LSTM network has different gates that selectively retain only important information over time. So this is useful for long-term time series analysis. So in short, we combine CNN for capturing spatial patterns with LSTM for capturing temporal dependencies. And we are going to use this model to analyze a particle distribution function for fields. So let's implement the model. So first, we need data from simulation. To make simulations, we need a physics model, 3D model. So as we discussed earlier, the simplest 3D model involves influx decay into Higgs particles. However, in order for this model to be captured in simulation, the coupling should be large. And Higgs is a good material for deep learning because it has both self-interaction and gauge interaction. So the distribution, each distribution should evolve in a self-similar manner. And so this model again has nothing to do with dark matter. So below are the simulation outcome. The first figure represents energy distribution of different fields. So the inflaton field dominates the total energy of the system, while Higgs particles are produced by interactions with inflaton field. And then Higgs particles soon share their energy with gauge bosons through SU2 times U1 gauge interaction. This is the picture of this model. And then we want to this is the actual deep learning code that we prepared. So we want to build a model by importing PyTorch library, and you can stack different layers in different hierarchies. For instance, the output of CNN can be received by LSM network or vice versa. So our model is structured in parallel. So each output of 2 layers is analyzed by the final layer in the end. Oops. And then we train the model using the training data, as you can see. So at each epoch, the deep learning model makes predictions which are compared with the test data. And but if you're training too long, the model would try to memorize all the patterns, so it will lose so-called kind of, let's say, predictive power. So to prevent this so-called overfitting, we perform early stopping when the model achieves the best predictive power. And this spectra is showing the occupation number or distribution function of the Higgs fields for the model we just discussed. And so the red spectra transition to the blue ones over time. And after some point, the spectra will show some consistent trend that can be learned by our deep learning model. So for training model, we use 15 points, but here we showed only 2 points in the IR and UV mode. And dotted curve represent data for training, and solid ones are predictions, which look reasonable. And by collecting all the predictions, we can obtain the evolution of the distribution function beyond the data range. And once it's trained, the predictions are almost instantaneous. So this way, we believe we can reduce our dependence on simulation data. And we can also discover some fundamental physics from using deep learning. This could be the subject of future work. So in conclusion, I'd like to conclude. So we learned that simulating the universe with HPC is useful and also interesting. And however, it costs a lot of simulation time and computing resources. So to overcome this, we try to integrate lattice simulations into deep learning techniques. And finally, as you can see from this year's Nobel Prize, the developments in the machine learning, deep learning, and AI are not science fiction, but really happening right now. So we have to think about how to prepare for the era of AI for the future of physics. That's it. Thank you.
Questions, please. You see, it is very nice presentation, and you see, we are mainly experimenting. So we are theoreticians, but we need to connect our result to some experiment. So you were talking about this gravitational wave search and other things. So we know that there is polarization of the B modes which are produced by gravitational waves. How we can connect to the B modes which can be measured through polarization of the microwave background to the results which you obtain. Because you see, your your calculations depend from potential, from many things. And so how we can select from the observational data what model is better and how we can get some adjustment. So it is a question. Because it is clear that you can do something interesting, but how to connect this interesting to what cosmologists measure?
I see. So the problem is that they are concerned in different scales. So we are focused on the, let's say, larger, events with the larger momentum scales than the scales of inflationary dynamics, for instance, B mode measurements. And
Yeah,
so
but
on.
anyway, you have some cosmic microwave background, which is 380,000 years old, yes? So it is, you know that there. So are your predictions related to that data? Because the cosmic microwave background comes later, but you can connect them because it is, you say that you get mass and everything adjusted from the CMB data, yes?
Well, let me think. But the CMB has to do with the scale of the universe, which is much larger than the scale of this particle interaction by depth inflation.
Yeah. But anyway, we need to connect to some other.
So it highly depends on the
It is
model.
not that you can explain something, but the results which are coming, they are resonant. But we
That's
need
why
to do something which should be verified. How we can verify?
That's why probing a gravitational wave background would be very important, because it could be measurable
Through
in the future.
polarization, through beam or
Spectra,
through spectra of what?
spectra of gravitational wave background.
But
This can be
because
simulated.
gravitational wave background you cannot measure because you don't have device. You have
We have experiments. Gravitational waves.
It is nanograph, you say, yes, nanograph or what? With
Including
pulsar,
nanograph, yes.
yeah, pulsar timing.
Is
So
one of them.
how from pulsar timing I can extract this from supermassive black hole mergers or something? So because they can give the same frequency, so is there any way? Because you use artificial intelligence, maybe there is some way to extract it.
Oh, yeah, that's a good point. I forgot to tell you that. There could be already some electronic signals in the data we already possess.
But I
The
think,
AI can be useful.
I think that in the plasma, you can create gravitational waves, but the frequency is 100 gigahertz.
Yes, that's the point.
It means that you need devices that don't exist right now.
Yeah. It is my question.
It's
because-
in the future, but
Yeah,
there are
in the
a lot of
future.
effort.
No, there are
We
some
have to give some
experiments.
suggestion to the
Yeah, to experiments
that
and.
they have to make very small devices that can measure subatomic level frequencies.
Yeah, but at the moment, there is this nanograph, so there are some experiments. But, okay, anyway, so it is my question, how to relate to measurements which people do.
Yeah, that's an important question. We need to. For which we need to find the answer.
Approach is good, so you are approaching very modern methods.
This back reaction effect that you were discussing seems quite dramatic, so there should be some way in the future to see some effect. There's a problem in gravitational waves. I don't know. Anyway, so you were, I have a question about your machine learning. how exactly do you train the model? I didn't understand exactly. Is it assisted training or what kind of?
It's called supervised training.
Supervised training. So it means that you feed some data
Yeah.
and you already know the answer. And
Yes.
then the code tries to
So you divide data into
Yes.
training set
training set and that.
and test data. Yes. You need
I'm confused because if you already know the answer, why you need to is to
because you
speed
want
up
to
the
go beyond. You want to go
But-
beyond.
Okay, but this implies an extrapolation. So how are you sure that your model is still valid if you go outside of the range?
That's why we have to compare it with the test data. Well, so you have to
need
believe.
also to test outside.
No, I mean here you can see. So we train the model in this region, and then we try to make the model tries to make prediction
Outside, and then you
Outside
double
test
test
data.
with some.
without any bias, and then we compare the prediction with test data.
Okay, so basically you use this to be able to extend your predictions beyond
Exactly. Yeah, that's the
the
one.
range.
And this is model independent, purely independent exploration.
As long as the model has some pattern.
Yeah.
So it can be just analyzed by the model. So we don't input any formula. This is one of the best advantages of using deep learning. Because we don't
So
hit any.
the parameter in the x-axis is what? Is time?
It's time.
Time. Okay. So you just continue to.
So we just take
the
this
system.
2 points and plot it here as a function of time. Because this is the spectra, the function.
So this is based on this self-similar evolution.
Yes.
So basically, the assumption is that the evolution remains self-similar also beyond that line.
Oh yeah.
What tells you that? So how do you know that is true? So no, I'm just wondering if you can really rely on this prediction. So it's an extrapolation. So if everything remains the same, it's fine. But
Yeah, maybe that has to be the, how do I say, predictive power of the model. So we are considering some either case. You know, each kind of initial work. So we just.
Self-similarity usually occurs in conformance method.
No, it doesn't have to be. I mean, it has to do with gauging pattern as well.
Any other questions?
Yeah, I was just wondering if there is a study about emerging learning study like that to CMP power spectrum, especially in the region of low angular momentum. So are you doing that or with study?
Oh no, I'm not involved in any such work. I'll be interested
Yeah, because
working
about
by
CMP of spectrum, especially in the low L value regions.
Mhm.
Actually, the power spectrum curves has some ambiguities because there's some large error.
Yes. No, I remember. Yes, the
Like
picture.
low
Uh-huh,
momentum numbers,
Uh-huh.
right? But I'm just curious about whether we can apply the same approach
Mhm.
to predict the low region curves.
Okay, that's an interesting idea.
Yeah.
But in this example, we also use trends in terms of time. But for that power spectrum, I'm not sure if we have some something related to time variable. Right? We need some kind of evolution of the spectrum. That's how we make predictions, right?
Mm.
Yeah, so we should think about it.